welcome back to these new sessions of the Journal Scribe. Today we have as a speaker Andrea Bontempelli. Andrea is a third-year PhD student and is tutored by Professor Fausto Giunchiglia and Andrea Passerini. And his interest includes, of course, machine learning, and in particular, his research interest include interactive learning, human in the loop in the context of open world domain, and human and machine alignment, of course. And I think that you can start, Andrea, immediately, so we cannot waste time. So when you are ready, you can start.
Okay. Yeah, thank you, Gianluca, for the kind introduction. So today I'm going to present one of our recent work, which is interactive label cleaning with example-based explanation. This is a joint work with Stefano Teso, Fausto Giunchiglia, and Andrea Passerini. So I will start by introducing label noise and what this means, why we have this problem. I will then introduce skeptical learning, which is an interactive protocol that addresses this problem. However, it has some limitations. So we will overcome this limitation by using explainable skepticism, which is our solution. And we will show it how it's worked in some experiments. So let me start with our setting. Basically, we have a sequence of examples and labels that arrive over time. So some application can be crowdsourcing, citizen science, interactive personal assistants. So imagine that you have a personal assistant installed on your mobile phone, which collects sensor data like GPS, accelerometers, and it tries to understand which is your location. To do so, the personal assistant needs to ask the user query, particular question about where are you, in order to learn to recognize the location of the user. However, this setting has a problem, which means the user might provide noisy labels. This is a well-known problem, especially in social science, where you have questionnaires and the respondent needs to answer questions regarding his or her behavior. However, it might be difficult for the person to answer due to memory bias or due to cognitive load, especially if you're asking questions about things that happens in the past. Difficult to remember what you were exactly doing and what was your value. Providing wrong labels has a big impact on the accuracy of your machine learning algorithm. And so you end up having a training set containing noisy labels, but also a model that is not able to have good predictive performance. The fraction of noisy label, of noisy annotation that we get from the user can be very, very high. For example, my colleague made a data collection. So they asked university students to install a mobile app which collects sensor data. And the user should answer a question about the current location or mean of transportation. And what they discovered in this data set was that most of the user answer with provide 20% wrong answer, and for some user even more, which means that very big fraction of labels that we get from the user can be wrong. So skeptical learning was introduced recently to address this problem. So skeptical learning is an interactive learning protocol, which the machine challenges the user when thinks that they receive a suspicious example. An example is suspicious if the likelihood of the model's prediction is much larger than the likelihood of the annotation. So for instance, the user might say that he or she is at work. However, by looking at previous or past example, the model can notice that it's not true and that the user is on party. So here, after spotting a suspicious example, the machine asks the user to double check the provided label. So basically here, we want to get the ground truth label directly from the user. Traditional, typical machine learning methods tend to get labeled and use it even if they are wrong. In skeptical learning, you are trying to spot this mistake and ask the user to provide you with the ground truth label. In most of the case, we are able to correct this mistake, especially if they are caused by inattention by the user. Especially in our application, the user is in interest of the user to provide good labels, since personal assistant that is trained on a good training set can provide a better service to the end user. However, one constraint that we have is that we need to keep a limited number of questions. So we cannot bother the user too much. We don't have to overload the user with too many questions. Otherwise, the user might leave the application. So let me explain a bit more about skeptical learning. So what happens is that we receive a new example, we make a prediction, and then here we have to check if the model is uncertain about its prediction. And here we have the first type of interaction with the user. So the machine asks the user to label new instances on which the machine is uncertain. After the acquisition of this label, we need to check, should ask the user to double check this label if this label looks suspicious to the machine. After that, we obtain, hopefully, a clean new label. And this is added to our training set, and then we update our classifier. So how these checks are implemented? So in a more recent implementation of skeptical learning, the decision to query the user depends on the uncertainty estimation provided by the set of Gaussian processes. Gaussian processes are non-parametric distribution over function, and the idea is the following one. We have one Gaussian process for each class. So the probability that an instance belongs to this class, so the probability that the class is positive is defined this formula. Here we can see the plot. So we have orange instances, which means are instances that belong to the class Y. And we have negative example, which are the blue dots. The black lines is the mean function that try to approximate these instances. So an instance that is in this place, the probability that is positive is given by this formula, which is a cumulative distribution function, which takes the mean and sigma. So the intuition is the following one. If the mean value is near 1, it means that that instance belongs to that class with high probability. Or if sigma is also small, it means that the instance belongs with high probability to the positive class. So the probability is given by these shaded purple areas. So using these properties, we can decide to query the user in order to get a label when the machine is uncertain. So the idea is the following one. We query the user if the probability that that instance belongs to the predicted class, that probability is small, so the machine is very uncertain. So it's better to ask the user to get a label. This query, so basically, the query is randomized. It means that we query with probability alpha t. This is in order to avoid to trust the uncertainty estimation of the model too much. After the acquisition of this label, the machine needs to decide if to keep the label that we receive from the user or to challenge the user. Again, here the different we are skeptical with probability gamma. So the idea is that the machine is skeptical if the machine is approximately equally certain about the predicted label and the annotated label. So if the machine is very sure about this prediction about that specific instance, but is also very sure that this instance doesn't belong to the class provided by the user, in this case, the user is challenged. More formally, we can say that the probability to be skeptical depends on the difference on the integrals of the Gaussian distribution of X on the predicted class and the user label. The probability that this difference is greater than 0. Okay, so far I introduced skeptical learning, which try to solve the problem of noisy label. However, it has also some limitation. The first one is that usually when you try your initial model is trained on a bootstrap dataset, which contain noisy data. And the model doesn't have the opportunity to clean this data, this noisy example that you have in your training set. So what happens is that this noisy example remain in your training set forever, and you don't have the opportunity to clean it. Which means that this also has an impact on the future ability to spot suspicious example, because new example that falls near a region where you have noisy example will appear good to the machine. The second problem is also that incoming example that elude the skeptical check also end up in your training set. And so to remind the impact of this noisy example in the data set is that also your predictive performance will decrease. Okay. Another problem is that this solution is completely black box. It means that the user doesn't know why the machine is skeptical, why the machine is contradicting the user. So there's no way to know if the model is skeptical for the right reason. Let me make an example. So suppose that the user say that is working. However, the machine look at some past example and find a past example that is very similar to the current incoming example, but has a different label. So the incoming example belongs to the class work. However, a very similar example in my training set belongs to the class party. But the ground truth is that the user is really at a party. So in this case, the counterexample, this past example that we have in the training set is correct, is clean, and the incoming example is wrong. So in this case, the machine is skeptical for the right reason. However, it can happen that the machine is skeptical for the wrong reason. Again, here, the user is working, and by answering the question of the personal assistant, she correctly say that is working. However, this example, so suppose the sensor data that we collect through the smartphone fall very nearby another example in our training set, which was labeled as party. In this case, we can notice that the skepticism is supported by a past example that is mislabeled. Due to, for instance, because there was a past mistake of the user or the user lied in the past. So how we can overcome this problem? How we can make solve this black box problem and also solve the problem that we may have a noisy example in the training set. So the idea is that when the machine is skeptical, we provide also some counterexample. What is a counterexample? It's basically a concrete past example that explains why the model is skeptical about a new incoming example. So counterexample is a training example that we use to support the model skepticism. What happens is that we can show this counterexample to the annotator, and we can let the user fix also this counterexample if it is needed. So we define 3 desiderata that the counterexample should satisfy. The first one is that the counterexample should be contrasted, which means it should explain why the incoming instance is suspicious. So by showing this counterexample, should be clear to the user, should highlight our potential inconsistency in the data. The second desideratum is that correcting this counterexample, by correcting it, we should improve the model as much as possible. And last, it should be clear to the user why this is a counterexample and why support the skepticism of the machine. So the question is, does such example exist? How we can identify them? So let's start from the first desideratum. So the counterexample should be contrasted. So should support the skepticism of the machine. And if we remove it from the training set, the model should be less suspicious. So the idea is that we should find this, we should find the counterexample that maximizes the difference in likelihood for suspicious sample pre and post removing the counterexample. So basically, we have our model, we train it on a training set which doesn't contain the candidate counterexample, and we take the likelihood. And then we take the likelihood of the model trained on the whole training set, which contain also this counterexample. So the counterexample that maximizes this difference is a counterexample that satisfies the contrastive requirement. However, this is quite impractical. So you need to retrain the model for each training example that you have. Moreover, you have to do that each time you have an incoming new instance. So it's quite impractical, especially in our scenario where we are interacting with the user and we are getting a stream of new example over time. So to address this, we can leverage inference functions, which is a tool that is used for robust statistics. And the idea is that inference function approximate the change in the parameters due to reweighting an example. So by reweighting a candidate counterexample, we see how much is the change in the parameters of the model. Okay, this is the formula. This applies also to non-convex model as shown in this reference. Here, H is the Hessian. So the change in likelihood that I showed in the previous slide can be approximated by using the inference functions, using the chain rule of the graph. Okay, so if we want to select a contrastive counterexample, we need to maximize this formula. So this part represents the inference function that we saw before. But the interesting part here is that this part of our objective is constant with respect to the specific counterexample. So it means that we can cache this part, and so we can speed up our computation. So only this part needs to be computed for each counterexample. Okay, so here, so if we solve this, we can find a counterexample that is contrasted. What about the second requirement? which is we want a counterexample that is influential. So if we train our model by minimize the cross entropy loss, it's turned out by rearranging this formula that we have seen before, by constructor, we obtain this quantity. Again, if we substitute this part in the previous objective that we have seen before, the one that we defined to select contrastive counterexample, we obtain this formula. And so basically, which basically correspond to this one. And this is match the definition of influential example that were introduced in this work. So what does it mean? This means that if we select contrastive counterexample, these examples are also highly influential. So it means that by reusing the same counterexample selection objective that we use for finding contrastive counterexample, we can find examples that are also influential, and vice versa. Okay. So the problem with influence function is that the Hessian here that we have here is not invertible. It's not invertible and make the influence function very unstable, especially in our setting where we have noisy data. So to overcome this, we replace the Hessian with the Fisher information matrix. So our counterexample selection objective that we introduced before, which is the maximization of this quantity, can be rewritten as this one. So basically, we substitute the Hessian with the Fisher information matrix. The Fisher information matrix, or FIM, has some nice property. The first one is that it's quasi-semi-definite. So the inversion of this matrix is more easy. The second aspect is that if our model approximates the data distribution, F also approximates the Hessian. And in our case, even if this doesn't hold, like in our case, since we have noisy data, the Fisher information matrix still captures useful information about the curvature. And again, the caching that I showed you before still works even in this case. The Fisher information matrix is a matrix which is the number of parameters of the model times the number of parameters of the model. So it's very big. So we restrict the computation only to the top layer of the neural network. So basically, we only use the parameters of the top layer of our network. And we call this top Fisher. And this solution helps us to speed up the computation. Okay, so far we have seen how we can select counterexamples that are contrastive and influential. what about the third one, the third requirement, which was pertains? So we should find an example that, so it should be clear to the user why a counterexample support the machine skepticism. The solution very easy is to select example in our training set that belong to the same class of the prediction. In this way, what happens is that if the incoming example is correct, it's likely that the counterexample is wrong, or if the incoming example is wrong, and if the incoming example is wrong and our counterexample is correct, probably the incoming example needs to be fixed. Okay, to explain this, let me make a couple of examples. So the user provide a new example which belong to the red class. And these fall into region which the classifier think is blue. And so the user is contradicted. In this case, the machine select highly influential blue example that support the machine's prediction. In this case, this example. And this is shown to the user. By providing this example, counterexample, we highlight an inconsistency in the data, and the user can correct this example by saying that is blue. Okay, so second example, again, the user provides a new example which fall in a region which is affected by this red example. So the machine in this case is skeptical because it thinks that this example should be classified as a red. However, in this case, the user has the opportunity to fix the counterexample, the example that was in our training set. In this case, we can improve the predictive performance of the classifier in this region. Okay, so we hand up correct this noisy training example. And so we improve our training set. Okay, I would like to show this example. So suppose that we have this image which represents a 4, and this is correctly predicted as a 4 by the machine. However, the user annotates this as a 9. CINCER, which is basically our approach, which provides a counterexample when contradicting the user, select a counterexample which is annotated as a 4 and actually is a 4. So in this case, we have a clean counterexample, and the incoming example is annotated wrongly by the user. So the suspicious example is mislabeled. In this other example, we have this 2, which is annotated correctly by the user as a 2. However, the machine thinks that is a 7. Why? CINCER, which is again our method, select an example which was annotated in the past as a 7 and which looks very similar to this 2. However, this counterexample is mislabeled. because it was annotated as a 7. And so you justify the machine, which predicts also these two as a 7. So in this case, the suspicious of the machine is supported by a mislabeled counterexample. And if we fix this counterexample, we are able also to fix the prediction for this, this image. Okay. So we validate. Yeah. Maybe I can just finish just a few parts and then we can. I will take question. Okay, thank you. So we validate our solution on few data sets, and we try to answer these research questions. The first one is, counterexamples are useful if we want to clean our data set, which is our first question. Second question is, which influence-based selection strategy identify most mislabeled counterexamples? And the last question is, what contributes to the effectiveness of the best counterexample selection? So we use both tabular data set and images. We corrupt our data set with 20% probability. And then we use 3 models: logistic regression, feed-forward neural network, and a feed-forward network with 2 convolutional layers. So in the first experiment, we compare our method, which is named CINCER, the red line, using top feature. So again, computing our feature information matrix only for the parameters of the top layer of our network. We compare CINCER against 2 other alternatives. The yellow one is drop counterexample. So we identify a counterexample. We don't show it to the user. We just discard it from the training set because it might be noisy. The gray line, which is basically no counterexample, which is, let's say, plain skeptical learning. We just say to the user that example, we contradict the user without showing any counterexample. And what we see here is that CINCER is able to achieve a better performance. And you can see the bottom row, red line. So here we can see on different data set and using different models. In the top row, you can see how many examples are cleaned by our methods. And again, you can see that the red line is always above the other competitors, which means that counterexample, fixing mislabeled counterexample help improve the performance of our algorithm and help improve our data set. So yeah, I didn't say it, this is the F1 score, bottom line. So the second question, want to compare different counterexample selection strategy. Here we have plain inference function. Top feature is our solution, and full feature is basically computing the feature information matrix on all the parameters of the model. Here, we wanted to see how many of the highest scoring counterexample are mislabeled. So we look at the first 5 and first 10 counterexample selected by this different strategy. And we can see that top feature is the best, except for the full feature, which, however, is impractical in our case because the computational cost is very high, so we need to compute the metrics for all the model parameter. So basically, using top feature is the way to go. Okay. In the last experiment, we compare again our method, top feature, red line, again 2 alternatives. The green one is nearest neighbor, which means when I have a new example, I take the nearest example to that, okay. Practical feature is another alternative of we can compute the feature information matrix. And again, here we can see that the red line is above the other competitor, both in number of clean example and according also to the F1 score. It's interesting to note that here, in this case, on this adult data set, nearest neighbor and top feature clean the same amount of example. However, there is a difference in F1 score, which means that top feature was able to find counterexample, mislabeled counterexample that are also influential, and thus can impact on the F1 score of the classifier, which means is looking around a suspicion example is not enough. You need to find counterexample that are also high influential. Okay, to conclude, if you take away, we show CINCER, which basically makes skepticism explainable. So basically, using an interactive cleaning strategy, we are able to clean bad training example in our training set. This is done by explaining why three desiderata, contrastive, influential, and pertinent. To speed up our the selection counterexample, we use the feature information metric, which is also more stable with respect to the Hessian. And so by using our method, our solution, we are able to obtain a better data set and to use better models. And we allow the user to reject or trust, establish or reject the trust in the model. Okay, that's it. Thank you.
So thank you, Andrea, for the interesting
Thank
talk.
you.
So now it's question time. So if you guys have any question, I think that you have. Yes, that's okay. Okay.
I don't know what this.
Maybe I would like to start from the contrast sample
Okay.
this one. So with this example, we were trying to explain us how somehow the machine tries to convince the user that the label provided by the user is wrong. So, for instance, this the first example with the flow, right?
Yeah, all right.
In this case, it's quite simple because the images that are something visual that the user can immediately understand what it made. What if the input data is a collection of thousands of sensor data that is hard to interpret? Maybe for the machine it's not hard, but for the user it's really, I think, hard to see, to be convinced that the label he or she labeled the example in a wrong way. So how can you generalize this approach? Is something different from you?
Yeah, thank you for the question. Yeah, it's true. If you have images, you can show two images, two examples, and so it's clear what is the inconsistency. If you have like sensor data or table of data, you should find a way to represent this example. So for instance, if you have a collection, I don't know, of GPS coordinate, you can show it on a map. However, if you have accelerometer data, gyroscope data, or other sensor, yeah, you have to find a way to visualize this type of information. So it's not trivial. You need to find a way.
Especially this, you have a collection of different types of different sources of data. Because if you have GPS data together with, I don't know, for temperature, humidity, how can you put them together and tell the user you were wrong, and you were wrong, because this data proves that you were wrong, and the label that are telling you is wrong.
Yeah, you need to find a way to represent this type of data that is application specific, I would say. But yeah, it's true. If you don't have image but tabular data, yeah.
Question. So suppose that you and you see your approach is still about if you have a bigger network. Because the usual this kind of approach as well. I would have
I repeat the question. If this approach works also for bigger model, so here the expensive part is computing the feature information matrix. So basically, you can restrict, which basically you can restrict only to a subset of the parameters of your model. So like in this case, we can so in our example, we restrict it to only to the top layer, to the last layer of our network. So one way to do is this one, this approach, so to restrict that. And also by caching, so basically this part, okay. By caching this part, which is independent of the candidate counterexample, you can cache it, so you need to compute this. There's also another way to speed up.
sorry, I interrupted you.
No,
See?
Yeah, yes.
so, I'm not, I have to be honest, I haven't heard about skeptical so I was curious, and so that's why I think so I'm a bit skeptical about the way the model is skeptical. So if I imagine a model classification stuff, let's simplicity that we have a binary product. 0, the user is a 1, the user is a 4. So, and the model, based on the data, predicts if the user is at home or at home. So, what the model does is compare the prediction, which is a number between 0 and 1, and the label given by the user, which is 0 or 1. Right? So, I have to admit, I didn't understand information about step.
Okay.
So, what I would do would be comparing the prediction, so the probability, the label, and use a kind of threshold if the difference is above a certain threshold. I would say, okay, user, you are telling me something around. This is not correct. I don't know if it is the same. So, I don't know if the formulation tells the same thing or something that there is something that is
This is correct. So basically, you compare how sure the machine is on its own prediction, so on its own predicted label, and how sure is on the label provided by the user. If there is a big difference, so the likelihood, as you can see here, so basically, if the predicted label, the probability of the predicted label is very high with respect to the label provided by the user, the machine is skeptical about the label provided by the user. I mean, there is an inconsistency. I mean, I don't trust the user because my confidence, the confidence of the model on the label provided by the user is very low.
So, only a comparison or the model could be also skeptical when the probability is close to, let's say that the threshold on the output of the model. So let's say 0.5. So 0.5, I say the user less than 0.5 user is at home, above is at home.
Yeah.
Then the probability is close to the threshold will be I'm not certain about the location of the user, and also this case I would be kind of skeptical. Not on the user label, the user what the user says, but also in my prediction. I'm also not sure about my prediction. So there are two levels of uncertainty.
Yeah, right. So you mean if, okay, let's say if the both class in our binary example, both classes have the same probability, so half and half.
Exactly.
Okay. In this case, okay. So let's say there are two implementations of statistical learning. I tell you about that one, which is based on.
This is the part of the
okay, yeah. It was a bit more technical, but I hope the high level overview was clear.
So if there are other questions,
no problem. In that case, if the difference between the two probability is low, the probability to contradict the user is lower because the machine is not certain about this prediction. So in this case, the probability that the machine is skeptical is lower. If the difference between the two classes is higher, in that case, the probability that the machine will contradict the user is higher.
There are two terms that certain things of the model and the comparison between the output of the model and the
Is always the probability is always the output of the model, but evaluated on the class that is predicted and the class provided by the user. So if the model predicts that I'm at work and the user say that is at home, the model classify that the user is that I'm working with confidence 0.9. The other class, the confidence of the model on the other class, which means I'm at home, is 0.1. It's always the confidence of the model, but on the label provided by the user. In this case, you see that in this case, the difference is very large. So in this case, also the probability that the machine is going to contradict the user is large, because the machine is very confident that its own prediction is correct. If they're both 50%, in that case, it's less. Very cool.
Okay.
I like the question.
I don't see any other question in the chat, so yes. Yes, I think that it's enough. We can close these sessions. I think it's the right time. So thank you guys for attending this seminar. And I think that we can close now. Thank you again, Andrea, for the interesting talk. And hope to see you for the next sessions. That probably, due to the period, is going to be the last one. But we are going to start again, I think, in September. So, guys, see you next time.
Thank you. Bye.
Thank you. Bye-bye.